The scale is difficult to process. An architecture operating with 2.4 trillion parameters has just been made public. This marks the first time a flagship Max-class architecture from this developer has been released with open weights. The weights for this system will be available for public download in exactly 1 week. Unlike previous open weight releases that required heavy human scaffolding, this system is built to execute complex, multi-day engineering and research tasks end-to-end on its own. It sustains this behavior through a closed-loop system, relying on continuous internal feedback to evaluate its own mistakes and rewrite its logic. By offering frontier-level sustained execution for free, this release directly challenges the economic moat of closed API developers. To understand how this system operates without human oversight, we need to deconstruct 3 extreme cases of its autonomous performance. The capability to solve complex, long-horizon problems is no longer restricted to a handful of proprietary servers. In the first case study, the model was given an empty folder and tasked with building a command-line interface project from scratch. It operated autonomously for 16 days. Without human intervention, the model produced 265 commits, submitted 127 pull requests, and resolved 151 GitHub issues. This chart shows the architectural engine making this possible, an integrated issue state machine. The model pairs this machine with a dispatcher and watchdog. When a new requirement enters the issue tracker, an agent claims it, writes the code, and cycles the state forward, converting community feedback into active execution. Before any code is merged, the model triggers its own unit and end-to-end tests. Any abnormal state or error log is routed directly back to the start of the loop for a fix. The model handles the entire continuous integration lifecycle of a human engineering team, rather than simply writing isolated code snippets. Software engineering is highly structured. For the second test, the model was pushed into autonomous algorithmic research, reproduction, and improvement of a complex AI data selection paper. The model received the text of the paper and access to raw GPUs. No starter code or pre-built data pipeline was provided. Over roughly 37 hours, the system designed the data processing scripts, configured the training code, and reproduced the paper's core findings from zero. This timeline maps the transition from reproduction to autonomous evolution. It shows a self-improving loop of forming hypotheses, launching GPU runs, and analyzing the resulting metrics. Across 4 rounds of research, the model independently invented and tested 18 separate improvement ideas, using the results of 1 round to inform the hypotheses of the next. By diagnosing its own failures, the model evolved a new data selection method that outperformed the original paper's approach on the AIM-2-4 math benchmark. The system demonstrated the capacity to move past mimicking existing research to synthesize net new algorithmic progress without human oversight. The third test forced the system to navigate rigid constraints of physical engineering, autonomous execution of a full silicon design flow without human reference designs. The target block was a highly dense cryptographic hardware accelerator, handling modular exponentiation. If you want more deep dives into how frontier models are being applied to engineering, subscribe to the channel. In digital circuit design, the goal is to minimize the synthesized gate count while maintaining bit-exact functional correctness across multiple configurations. Starting with empty module templates, the model operated in a sandboxed environment for 500 iterative turns, managing its own simulation and synthesis toolchains. When the model realized its design was bloated by an expensive hardware modulo divider, it replaced the entire block with an iterative shift-subtract architecture. That algorithmic rewrite slashed the design by over 6,000 gates, proving the system can re-architect a data path rather than just adjusting syntax. It continued with aggressive gate-level refinements, pruning redundant registers, narrowing bit widths, and merging submodules to eliminate logic duplication. This graph tracks the optimization trajectory. The model drove the total size down from a starting point of 8,298 gates to just 678. To verify these software-level gains translated to physical hardware, the design was run through a standard place and route flow to generate a silicon layout. The initial 106 by 106 micrometer die shrank to a 46 by 46 square. The final die was 81% smaller and successfully achieved timing closure at 500 MHz. Software-based language models can now independently execute and validate complex optimizations in the realm of physical engineering. Sustained, self-correcting behavior is the result of the underlying architecture that enables these feedback loops. The core challenge in training an autonomous agent is reward assignment. When a workflow stretches across multiple days, assigning a reliable reward signal is difficult. The engineering team addressed this by jointly scaling complex environments alongside compute, driving the model through deep reinforcement learning. This diagram shows the central mechanism, a universal reward system. It unifies code execution checks, text evaluation, and visual outputs into one coherent signal. To keep this stable during prolonged training, an online data balancer shapes the batches to suppress gradient variance across different tasks and difficulties. We can measure how this open engine performs against the proprietary frontier through a technical audit against the current leader, Fable 5. This chart compares top models on key benchmarks. Qwen3.8-Max records clear victories here, logging a 93 on Paperbench and an 86.1 on OS World Verified, ahead of its closed rivals. The audit also shows remaining gaps. It still trails Fable 5 on specific coding evaluations like SW Bench Pro and Frontier SWE. However, it shows dominance in multimodal reasoning, scoring 95.2 on MathVision and leading the field in long-horizon application recreation. The model's API pricing is $2 per million input tokens, a rate that directly challenges the profit margins of proprietary providers. The combination of this reinforcement learning architecture and aggressive pricing changes the cost-to-capability calculation for enterprise AI integration. In exactly 1 week, this entire 2.4 trillion parameter system becomes public. The model weights will sit on open platforms like Hugging Face, ready for any developer to download, audit, and run. For systems builders, this removes a critical dependency. They no longer have to rely on opaque, rate-limited proprietary APIs to orchestrate a multi-step agent. Engineering teams can now take this massive, self-evolving architecture, fine-tune it on their own data, and deploy it entirely within private infrastructure. It forces a question for the current market leaders. What is the value of a closed-model enterprise subscription when frontier-level autonomous execution is available for free? The model moves frontier-level capability from closed APIs to open weights, placing these autonomous systems directly in the hands of developers.